In this recording, we discuss capacitors in series. Capacitors are connected in series when they are connected end to end. First one, so this is the end of the first one, and then the end of this other end of that first one is connected to this end of the second one, and the end of the second one come last. So they are one after the other. Now, and this type of connection, since charges have nowhere else to flow, if I collect a positive charge plus Q here, of course for a capacitor I'm going to have a minus Q here. Now this part here that I'm going to highlight in red, it's not connected to anything else, meaning that the charges here should remain balanced. I should have an equal number of positive charges as of negative charges, which means if I have an accumulation of negative charges here, I should have a corresponding equal number of positive charges here. Now, if this upper plate of the second capacitor has a plus Q charge, then the lower plate obviously has a minus Q charge. What this is telling us is that both capacitors have the same charge Q. And overall, from the outside, all what we are going to be able to see is going to be either a plus Q from the top or minus Q from the bottom. So the equivalent charge for both capacitors in series is just Q, the charge in one capacitor. Excuse me. Now, what about the voltage? The voltage across the capacitors is going to be the voltage from here to here. So that's going to be, let me see if I can erase this. Okay, we're clean again. So the voltage across this capacitor is going to be V1, and then the voltage across this capacitor V2. So overall, if I would like to replace these two capacitors by an equivalent capacitor, I need to have a voltage difference that's the sum of these two between these two ends. That's my equivalent voltage. Now, if you remember, Q is CV, meaning that V is equal to Q over C. Now, what that means is, if we go back to this equation, V equivalent, which is Q equivalent over C equivalent, is going to be equal V1, which is Q1 over C1, plus V2, which is Q2 over C2. And since Q1 is equal to Q2 is equal to Q equivalent, all these are going to cancel out, and we end up having this. 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So the equivalent capacitor for two capacitors in series has a capacitance given by this expression. Now, if I have 3 of them, it will be plus 1 over C3, and so on. Now, how would this make sense? Remember again the expression for capacitance. C is equal to epsilon 0 A over D. By putting two capacitors in series, it's like increasing D. Instead of just having D1, I have D1 and D2. And where are the D's? They are in the denominator. So when do the D's add up? Like here, I'm adding up the two D's. If I get the inverse of all of this, so 1 over C is going to be D over epsilon 0 A. So you see here where 1 over C1, that's going to be D1 over epsilon 0 A. 1 over C2 is D2 over epsilon 0 A. Now the D is equal to D1 plus D2. Okay, that's the idea. Just a conceptual way to look at capacitors in series. Let's look at this example here. If we take our 4 microfarad capacitor and 6 microfarad capacitor and we connect them in series and subject them to 5 volts, what would we get for C equivalent? So for C equivalent, what we do, 1 over 4, 1 over C equivalent is 1 over 4, the answer is going to be in microfarads, plus 1 over 6. So I'll put these in the same denominator, so I'm going to multiply this by 3 and this by 2. So I have 3 plus 2, 5 over 12, so C equivalent is going to be 12 over 5 microfarads. Notice that the 12 over 5, what's 12 over 5? It's going to be 2.4. 2.4 microfarad. It is smaller than either capacitance. That's key. So when we put two capacitors in series, we get a smaller capacitance. So if I would like to have a small capacitance that I have only large capacitors, I can place them in series to get a smaller capacitance. Excuse me. And then what's the charge? Charge is C times V. So here, since we know only the voltage across both of them, we can find the charge in both of them. So that's going to be 2.4 microfarad times 5 volts. So that's going to be 5 times, so that's going to be 12 coulombs. No, 12 times 10 to the minus 6 coulombs. Sorry about that. 12 times 10 to the minus 6 coulombs. And the charges are the same for all capacitors, since they are in series. Okay, before going on, let's compare these two capacitors in parallel, and let's look at them in a simulation view. Now, in series, now here I connected a circuit. I'll go to the circuit in 1 second, but I have a battery. I have a resistor to control the amount of current in the circuit, and this is one capacitor. One end is connected to the resistor, the other end is connected to the other capacitor. Now, the other end of this second capacitor is connected back to the battery. The key here, what you need to notice, is between here and here, between this end and this end, they are somewhat isolated. Meaning, no charges can come in here and no charges can come out of here. So if I get a certain amount of charge in this plate, I should have the opposite charge in the other plate so the charge remains balanced. And you notice here I have a plus here, minus here, plus here, and minus here. And you notice even in the simulation, the charges, they look equal. Now, if I connect them in parallel, how do we connect in parallel? Both ends of the capacitors should be connected to each other. See, this end is connected to this end. And this end is connected to this end. Okay, now the bottom ends, both of them are connected to the negative of the battery. They have a negative charge. Now, the top end, both of them are connected to the resistor, and you see they have positive charge. And notice the charges. I have a larger capacitance here, so I have a larger amount of charge than here. Okay, let's go to the simulation and look at it with the simulation. Here we go, it is running. What I'm going to do is just break the circuit for a second and discharge the capacitors. It is interesting the way it is working. It's working really nicely, but discharge. Now I'm going to connect. What was happening is the charge from one capacitor was going to the other one and vice versa. Okay, now here it's going to be easier. Split junction, discharge, and discharge. Okay, now let's pay attention to what's going to happen for the case in series first. The minute I'm going to close this, so you are going to notice that this one is going to charge up positively and this one is going to charge up negatively, while charges are going to come up here positively. Okay, see there the charge build up, and we have equal charges and a small charge overall. Now look at this one instead. Okay, see here, this is building more charge than this one, and overall I have more charge here than here, and the overall amount of charge collected is going to be the sum of both of them. Now if I pull in a voltmeter and put it here, what I'm going to try to show that both of these ends are at the same electrical potential. That's why we read 0 the whole time I move from here to here. Now the other ends are also connected. So here I'm reading 9.8 or so volts, and I'm going to read that same value hello. I should be reading the same value, 9.96. See, I'm reading the same value throughout the wire here, telling me that the wire is at the same voltage. Now, voltage across this capacitor is about 10 volts. By the way, the discrepancy was happening since they were still charging, they were not fully charged. Now they are. So I have here 10 volts, and I should read the same value, 10 volts here. And as I move this around, I have 10 volts throughout. Okay, however, for this case, now when I move to the other end, I have 6.67 volts. Okay, negative just because of the way I put the leads. So if I put them the opposite way, we would read 6.67 volts. Now the voltage across the second one is going to be 3.33. It's much different. It's actually half as much because we have half the capacitance. Okay, so the voltage across them is different. The charge is going to be the same. One thing I would like to point to before we finish with the simulation, the current right now with the circuit is 0. Once the capacitors are fully charged, It's essentially a break in the circuit, and there is no more current flow. See that? In either circuit, I don't have any current. There will be a current flow only if we allow the capacitors to discharge now, or at the time when we were charging them. One last thing about capacitors in series and parallel. To determine if two capacitors are in series, you need to be able to follow with one wire from one element to the other with no branching in between, so it's only one path from one to the other. You can have other elements in between, that's all right, as long as it is a unique path from one to the other. Now, for parallel, we have different paths to go from here or here. But what you need to do is you need to be able to come up with one loop that includes both elements, both devices, both capacitors, but no others. You need to find one loop, just one loop, that includes both devices but no others.